Okay, so we usually start on time, so let's start on time today as well. So good afternoon, everyone, and welcome to the first half day of the workshop Topics in Quantum Gravity, co-organized with the École Normale. Today's session takes place at the Collège de France. Tomorrow's session will take place at the École Normale, and the directions are on the website of the conference, of the workshop. Okay, now today's session takes place here because it has been inserted in my teaching at the Collège de France. It's actually the last day of my 2022 course. And also this explains why I am speaking at this workshop, even though I am a co-organizer. So let me just say a few words in French first to the students, and then we start and continue in English. Donc c'est la dernière séance du cours. Les leçons, disons, officielles se sont terminées la semaine passée. Et donc aujourd'hui, c'est une après-midi un peu spéciale, puisque c'est trois séminaires, tous les trois liés de manière proche ou plus large aux thèmes qui ont été abordés au cours. Bon, le mien sera très proche. En fait, c'est un peu à moitié leçon, moitié séminaire. Ce sera la continuation de ce qui a été vu. Les deux autres abordent des problèmes qui sont plus éloignés. Ce sont des vrais séminaire de recherche. Alors, je pense que c'est à peu près tout ce que je voulais dire avant de commencer. Donc, on va repasser à l'anglais. On a 3 séminaires d'1 heure et il y aura une pause après le deuxième séminaire. So, yes, for the program, we have 2 seminars of 1 hour each, and then we have a break, half an hour, and then the last seminar by Edward Witten will take place by Zoom. Okay, so let's start with the first seminar. The speaker is Daniel Jafferis from Harvard University, and he will talk about stringy ER equals EPR. So,
well,
thank you.
Thank you so much for the invitation to speak here. It's a pleasure to be visiting Paris, as always, and to speak here at the Collège de France. So I'm going to tell you about some work that is mostly based on this paper I wrote with my former student, Elliot Schneider, and this other paper with my student, Nick Agia, and some work in progress with Nick and Janelle Helder, a postdoc, and David Kolschmeyer, another former student of mine. So the idea is that there is this concept that sometimes goes by the slogan ER equals EPR, that connected space is built out of entanglement. And the idea here is to try to understand this in a more microscopic way using string theory. That's kind of the general idea. And so I'm going to explain to you how this ER equals EPR correspondence, first briefly what it means, and how it could be understood as a kind of string duality. And the example that I'll mostly talk about involves string theory in ADS3. So I'll try to explain how the ADS3 spacetime, which is some connected geometry, can be made out of an entangled superposition of microstates in some disconnected pieces of space. So it's the theme of this ER equals EPR is that entanglement between disconnected regions somehow sews them together, which sounds a bit surprising, and the hope here is to have a more explicit microscopic example where one can really understand how it works. And that's kind of the goal. But part of that is going to involve, in a sense, a new piece of formalism of how to do string theory in a certain context. And so that's a key ingredient in how this microscopic description, this stringy description, works. So that's what these 2 sections are about. And at the end, I'll sketch something about how this might be related to the idea of counting the states that make up black holes. So, black holes look like, solutions of the classical Einstein equations, or it could be Einstein gravity plus other stuff, and they are supposed to have a large number of microstates that are given by the Bekenstein-Hawking formula, an entropy that's related to the area of the horizon. And I'll describe how the kind of stringy configurations I discussed might be relevant for counting those states. So, but we'll come to it toward the end. Right, so the origin of this ER equals EPR idea is from the ADS-CFT correspondence, which is this correspondence between quantum gravity and anti-de Sitter space, quantum gravity in a kind of box, and a quantum system that we can think of as living at the boundary of this box. And so that was formulated more than 20 years ago by Juan Maldacena and in some particular example, and it's been understood a lot since then. And now I think of the ADS-CFT correspondence as not really arising from very, certainly we have explicit examples where we have a completely specific CFT and a completely specific ADS background with some string compactification, but the story is much more general than any of these specific examples. And really one can understand why it's supposed to be true from the point of view of quantum gravity itself. So if we think that we put gravity in a box like anti-de Sitter space, because gravity has the Hamiltonian constraint equation, so the time evolution in the interior is a gauge symmetry, so the Hamiltonian is a boundary term. And so therefore, if we look at the boundary extrapolates of things in the bulk, and then we ask how they evolve under the Hamiltonian, well, the Hamiltonian is a boundary operator, so it looks like the boundary is a self-contained system, which is just equivalent to the whole bulk. And that's kind of the idea of ADS-CFT, right? And one of the curious things that this correspondence implies is that if we have a space-time with multiple boundaries, then ADS-CFT will tell us that the Hilbert space of quantum gravity in this space-time with multiple asymptotic boundaries is a tensor product of Hilbert space associated to each of the boundary components. And that's kind of surprising because it would say that the connected bulk geometries, something which looks like a single spatial slice with multiple boundaries, is somehow a state in the tensor product of a bunch of boundary-anchored Hilbert spaces. But if we look at a factorized state, a specific state in each boundary Hilbert space, then that's dual to some configuration in each separate ADS component that don't talk to each other, right? Because if we have a state that's not entangled in a system with no interactions, then the different bits of it have nothing to do with each other, and we just apply ADS-CFT separately to each piece. So it means that there must be a bulk correspondence, without thinking about ADS-CFT, that every bulk geometry that looks connected must somehow be expressible as a linear combination of bulk configurations which are not connected. So that's the idea of ER equals EPR. And then this Ryu-Takayanagi formula that's a bit more general than the Bekenstein-Hawking entropy formula, which says that the entropy of black holes is the area in Planck units, area divided by 4 in Planck units. This Ryu-Takayanagi formula says that the entanglement entropy, if I take some factorization of the Hilbert space, is again given by the area of a bounding surface in Planck units. And so in particular, it's UV finite. So in other words, if there is no singularities in the entanglement entropy in gravity coming from short distances near the place where you cut space into pieces. So that's again a statement that the Hilbert space in gravity actually factorizes. So if I somehow cut space-time into two chunks, the state that describes the connected thing is living in a tensor product of two separate Hilbert spaces. But of course, this splitting of space-time gives a huge number of states because there's supposed to be this big entropy of the area in Planck units, so that means there are exponentially many microstates when you split it, but somehow they're supposed to sit together. And I mean, a very simple example is this two-sided black hole. This is the Penrose diagram of the eternal ADS black hole. And It has the Einstein-Rosen bridge, a non-traversable wormhole where if you can meet in the interior jumping in from the two sides. And this space-time is dual to the thermofield double state, which is an entangled state in two separate Hilbert spaces. This is an energy eigenstate on the left, that's an energy eigenstate on the right, and we have this superposition of them. The fact that it's a superposition is why it's an entangled state, right? So the two CFTs don't interact. They don't interact because there's no causal path between this boundary and that boundary. So they're causally disconnected boundaries. The theory kind of, in a sense, lives there. So we have two separate systems, and then this entangled state, and the gravity dual is this connected space-time. So that's what ADS-CFT tells us in this scenario. But there's something a bit puzzling about it, because if, each one of these states in the sum is surely a disconnected geometry. It looks like an energy eigenstate, black hole microstate on the left, and another one on the right, and they have nothing to do with each other because they're two separate states and two systems that don't talk in any way. But if the entangled superposition of them becomes connected, it means that some aspect of geometry, even as basic an aspect as the connectivity of space, is encoded by entanglement. It can't be described by a linear operator, right? Because if the connectedness operator is 0 on every one of these states, it will be 0 on the linear combination by the rules of quantum mechanics. So for example, the number of connected components of space-time is somehow not a well-defined ordinary operator of quantum gravity. And that is a rather surprising conclusion here, and there might be a variety of ways to understand what that's telling us. But one possibility is that we should think of this correspondence as a type of duality, in the sense that there are, maybe we can say that there are two somehow equivalent descriptions of the same space-time. One of them is a linear combination of factorized states. The other one is a connected geometry, and they're equal. So that would be a kind of duality, equivalence of these two descriptions. And we know, of course, in string theory that geometric features may not be invariant under dualities. There are things like T-duality, which relate space-time, strings propagating on manifolds that have different topology. But from the point of view of the strings propagating on them, they're exactly the same. So the question here is, can there be an explicit string duality between the entangled sum of disconnected spacetimes that look like the microstates and this connected wormhole? So that's the question that I'm going to try to address today. And I should say this applies not only to black holes, but even empty space. So if we look at, say, ADS spacetime in Rindler coordinates, the ADS Rindler spacetime is the planar limit of the 3D BTC black hole. So we can view, just like in flat space, in Rindler coordinates, it looks like it looks like a two-sided thing because there are two patches. And if we apply the same logic there, we would have to say that even the global ADS looks like a somehow linear combination of states in the two halves. Now, in the Rindler case, of course, because the Rindler horizon goes all the way out to the boundary, ultimately, there is some infrared singularity that looks like a UV singularity from the point of view of the dual CFT that makes it a little more subtle, so the CFT won't factorize. But if we imagine something that's not quite ADS in the asymptotics, but maybe the dual theory is not a CFT, but a lattice theory that flowed to a CFT in the IR, the asymptotics would be a little complicated, then everything would be completely finite, and we would have this kind of picture. But if we just look locally, there's not a big difference between ADS Rindler and the BTC black hole locally. It's just that one of them extends all the way. So I'm going to give an example of a duality of this type for the ADS3 string theory, strings propagating in ADS3. And the story really has two aspects. I mean, one of them is a worldsheet duality, which will be related to the Euclidean continuation of the spacetimes. And that's kind of novel for the ADS3 case, but it's very similar to something called the FCC duality that's been understood for a long time, which is related to a two-dimensional black hole instead of ADS3. But the other part of the story is a general framework for the Lorentzian meaning of the Euclidean duality that I will describe. And that's more novel and involves a new kind of string Hilbert space that's related to something that people called long strings. So that in a way is the main new thing, although this worldsheet duality in the ADS3 case is also new, but it's similar to others that were understood already. So those are kind of the two aspects. And maybe to say again, what's kind of the dream here? The dream would be if you could write a complete or maybe overcomplete, right? We might not write a configuration, in other words, we may write configurations which have non-zero overlap between them, but we can write a complete or overcomplete collection of factorized microstates and see an equivalence between the entangled superposition of them and the connected spacetime. Then you'll have a complete understanding of this story of entanglement building in space. And the first step here is to try to describe string perturbation theory around the entangled combination of the microstates. That turns out to be much easier than describing string theory or describing any of the individual microstates. So maybe that's not too surprising. It's a little bit like the fact that the thermal ensemble is simpler thing to understand than any particular fine-grained microstate. So that's what I'll talk about today. And so in the duality, I'll talk about one side. The Lorentzian target space will consist of these two disconnected pieces, but it will have an entangled superposition of microstates, and I only really know how to describe strings in that special entangled state. But I'll discuss some initial attempts to understand what the individual microstates look like in this picture. Okay. So that's sort of the, oops. Here we go. Now, let's get in, where did Euclidean come into the story? So the hope, right, was to find an equivalence between this Penrose diagram, the two-sided black hole, and something like this, where the green lines is an end of space. You know, it could just be the smooth origin of polar coordinates, or it could be a D-brane, or a region of strong coupling. There are many possibilities. Something that ends the radial direction. The middle here is nothing, right? This is just one space. This is another separate piece of space. But there's supposed to be an entangled superposition, and you want to find this equivalent to that. Now, how can we produce this state? We produce it by a Euclidean path integral like this that looks like the disk, hyperbolic disk. And if we cut it down the middle, then that glues onto the slice here. Okay, so that's the usual way of preparing the the black hole state, the Hartle-Hawking state of a black hole. On the other hand, how would you prepare a thermally entangled, that is the TFD state of these disconnected things? Well, I would take this annulus and cut it along the line here, and so then this strip glues to this, and this side glues to that side. So this is a diagram that prepares an entangled state and disconnected space-time. This one makes this connected space-time. And the big difference is that the circle here, which is the Euclidean time circle, is contractible on the left, but not on the right. Okay? So when it's contractible, the Lorentzian continuation gives you a horizon and the geometry is connected. If it's not contractible, it's more like what you usually think an entangled state is like, two separate systems that happen to be in a special state. And then I can draw this picture from the side. I mean, the disk is the same as this cigar, and the annulus is the same thing as a cylinder. But maybe this is a more familiar way to draw it. And In string theory, there is a clear way to see why one of these seems different than the other, which is in this Euclidean picture, I can take strings that wind around the Euclidean time circle. And it's not very obvious what that means in Lorentz signature, and that's going to be what that means in Lorentz signature is going to be a big part of what I'm going to say today. But if I look at those strings, then here the winding around this circle looks conserved because you can't unwind them, but on the left you can unwind them around the tip. And so it seems that the time winding is broken on the left, but not the right, so how could they ever be equal? So even this kind of Euclidean analytic continuation of the duality sounds like it won't work. But there are three ways that the figure on the right can break the time winding symmetry in order to be conceivably equal to the figure on the left. One of them is that you could have some strong coupling at the green line. Maybe it's a region where you don't have any control over anything and you don't know what happens, so that's conceivable but not very helpful. Another possibility is that there could be a D-brane wrapping the green line. Then you'll have open strings, and at one loop, the wound strings can break apart. And then the other possibility is just that there is an explicit winding operator added to the worldsheet theory so that you break winding explicitly. And that's what's called a winding condensate, and that's what I will talk about today. In a way, it's this, in some way, the simplest. Well, this is clearly a non-starter to actually understand anything. But in a way, this third option is the simplest because it involves, at least in the Euclidean picture, only closed strings, and there isn't any need to somehow cancel a one-loop effect with the tree-level effect on the other side, which would make that sound more difficult. And maybe another way of thinking about what is the green, like what should the green thing be in general, is we can have ADS solutions of many different types in string theory. So we usually get them by looking at the near horizon limit of some kind of object. So for example, the near horizon of D3 branes is ADS 5 times S5. The near horizon of fundamental strings on NS5 branes looks like this ADS3 background at the pure and never Schwarz point. That's what we'll talk about. And so it's natural to imagine that the green thing, which represents some kind of microstate configuration, is made of the ingredients for which the ADS spacetime was the near horizon. So if we tried to do this in ADS 5 times S5, we would probably be in this situation, and the green line would be some stack of NS5 branes. But that will be very complicated to study because there'll be an enormous number of them, and they won't be very weakly coupled, so it's a kind of a difficult hybrid description. But in the case of the ADS3 at the Never-Schwarz point, since it's like the near horizon of fundamental strings, we would expect that the green line is made out of something that could be understood just on the worldsheet. And so that's the idea of this closed string duality that I'll talk about today, and its Lorentzian meaning. So maybe to say a few words about what the ADS string theory is as a quick review. If we can study string theory with target space ADS3. Here's one coordinate system for ADS3. And in order to make a nice string background, there has to be H3 flux, some three-form flux. This is the two-form potential for that three-form flux. And this background solves the equations of motion. And if we take the sigma model with this background, say just the bosonic string, it's equivalent to having the SL2R WZW model, CFT, as the worldsheet theory. And that can be seen in many ways, like you can start on the WZW model side. It has this kind of Lagrangian. This is just the kinetic term, and then there's the Western-Minot term. And you can write the group element in some basis. SL2R, the group manifold SL2R is the same as ADS3 as a geometry. And so it's not too surprising that since the WZW model is a map from the worldsheet into the group manifold, that this thing ends up looking like a map from the worldsheet into ADS3. So if you write the matrix like this, that's how it obeys the embedding formula. This defines ADS3 as a hypersurface embedded in one higher dimension. And in this story, you can compute string scattering amplitudes, and in particular, there are certain kinds of worldsheet vertex operators which correspond to insertions out at the ADS boundary. So you can compute the kind of thing that you would calculate in the ADS CFT context from a worldsheet computation. And if we go to Euclidean ADS, that's some analytic continuation of the previous slide, and it can be described by SL2C mod SU2 coset. Basically, you want to have a Hermitian matrices instead of the SL2R matrices. And then you'll get Euclidean ADS3, which is this hypersurface. And again, or more specifically, if you take the vertex operators on the worldsheet, which are functions of some worldsheet coordinate xi, and the space-time coordinate x, then there's a field x, which depends on the worldsheet coordinates, and a field r, which depends on the worldsheet coordinates, and at large k, where k sets the curvature of ADS, so large k means weakly curved ADS with a large flux number, the vertex operator basically takes this form, or x is a parameter, and j is a parameter, and this thing is a mode function in ADS. It's a solution of the ADS wave equation. And these operators have worldsheet weight given by this formula, but they have dimension 2j with respect to the current algebra that generates the symmetries of ADS3. And so they look like a dual CFT operator with dimension twice j. Okay? So this is a this is an old story. And then if you want to get the Lorentzian correlators, the way the computations are usually done is you do a Euclidean computation, and then you analytically continue in the variable x, which is the boundary coordinate variable. Now, we can also discuss string theory in the BTZ black hole. The BTZ black hole is just an orbifold of ADS3 if we think of ADS3 in Rindler coordinates, then it's the quotient of the non-compact direction along the Rindler horizon. So it's like a spatial translation in Rindler coordinates, and this acts in a particular way on the group element. And again, we can get it by analytic continuation from Euclidean ADS, which is the thing that looks like, if we think of Euclidean BTZ, looks like a solid torus or a bagel, and if we cut it in half along the center, that's the continuation that leads to the BTZ black hole. Now, in addition to the states that look like the insertions on the boundary in Lorentz signature, there are also normalizable mode vertex operators that look like states in the theory rather than operators that you acted at asymptotic infinity. And of course, the normalizable states in BTZ are not related in any very simple way to the list of boundary operators. So they're, they correspond to like the modes in quantization of fields in the BTZ black hole. So those things are also in the game. They'll play some role eventually. And maybe to illustrate a general point, when we discuss string theory, we usually don't make a big deal about what state we are talking about. That's because in the standard string theory is defined in asymptotically flat space. We compute scattering amplitude. It's implicit that we mean that we put a few excitations on top of the vacuum. But especially if we talk about ADS target space, then we can consider many different states in ADS, because the dual is not an S matrix, but a CFT on the boundary that can be in different states. And how do we describe string perturbation theory on different states? Well, in general, that's a very hard problem. It's hard to answer in the standard worldsheet formalism. But it's not quite true that the worldsheet formalism tells us how to do string perturbation theory on top of classical geometries, and that doing perturbation theory on top of some other state is something we don't understand. What's really true is that we define string perturbation theory with Euclidean target, and then analytically continue the answers. And so a standard possibility is that we have a Euclidean target whose analytic continuation defines the vacuum state, but we can also get other kind of states, and I'll come back to this point in a bit. We can also define other kind of states, so we can take, again, this solid torus. Now if we slice it this way, this, if we were doing ADS-CFT, this path integral on the boundary annulus will produce the entangled state in 2 copies of global ADS. And if we fill it in like this, it's not producing the black hole, it's just producing a thermal gas, entangled thermal gas in 2 copies of ADS. This is one ADS cylinder, this is the other one. And this is, would be the dominant contribution below the Hawking-Page transition, when we just have, gas of gravitons or other particles in ADS. But we can do string perturbation theory around that Euclidean background and analytically continue this way. That defines string perturbation theory in the thermal gas in ADS, for example. And people discussed, going back to Attic and Witten and earlier, how to do string theory in the thermal ensemble, but in ADS, somehow it's especially simple because there's no infrared divergence, as there would be in flat space. And in this story, it's crucial that, say, if you want to compute the boundary correlators in the thermal state, that you start by, inserting an operator in the Euclidean section, do the computation, and then continue it to the Lorentzian piece at the end. Because otherwise, it would seem that there could be confusion because the Euclidean time direction is a circle here, you might think that if we have real Lorentzian frequencies, they're not compatible with the periodicity of the circle. So that's an issue that I'll come back to in a little bit. Now, okay, so that was a lightning review of string theory in ADS. Let me tell you what the Euclidean duality would be, and then I'm going to explain what's the Lorentzian meaning of these kind of dualities. So again, this is going to be very analogous to the FCZ duality, but it's, I think, a little novel in this ADS-3 version. So, okay, so if we consider string theory with ADS target, which was the same as the WZW model, we can also write it in Poincare, in the first order formalism. If you did that in the Poincare patch coordinates, where ADS-3, just had the exponential function that modulated 2 of the directions and then the third one, as a function of the third one, then that gives you, if you write the worldsheet sigma model in the first order formalism in Poincare patch, you get something that's called the Wakimoto Lagrangian. That's very, familiar. But here we want cylindrical coordinates because we want it to connect to ADS-Rindler and to the BTZ black hole. And so we have, in cylindrical coordinates, I mean this coordinate system for ADS-3, but which is the usual one if we thought it continued x to be time, that would just be global ADS-3. But now we're going to continue tau to be time, and that gives us ADS-Rindler. And if we identified x periodically and continue tau to be time, that's the BTZ black hole. So if we take the sigma model into this target with the B field, and we can rewrite it as a first order worldsheet action, where chi is the conjugate variable. Okay, so if we integrated out chi by completing the square, it will bring into the action some term that looks like sinh squared, and that will give the sinh squared d tau squared, and it will combine with the 1 here to give the cosh squared. So that's how it works, very simple. But now in the first order formalism, it's very nice for describing the ADS asymptotics because, in the sigma model on this, with this metric, as R goes large, which is going toward the boundary, the sigma model looks like it's getting very complicated because the metric appears in the sigma model action, and it's getting very big. So it makes it look like the action is blowing up at the boundary. But in the first order formalism, now the R dependence is just this 1 over sinh squared, so it looks like the term is getting tiny as we go out to the boundary. So this first order description is somehow very good near the boundary, and it becomes more complicated in the interior where this term is more important. And another point is that if you didn't have the last term, then the thing would just be a free theory. So there would be no interaction terms at all. It's a quadratic Lagrangian except for this piece. And you can kind of think of that free theory as telling you something about the conformal structure of the boundary, actually. Now, I'm going to just say what this duality is, because in some ways the main point here is the methodology to interpret these time winding operators, rather than the details of this specific duality. But let me just tell you in the slide what's the story. So the idea of the duality is that you want to replace this last term, which is the thing that ultimately capped off the Euclidean time circle, right? This is the thing that generated this sinh squared term here, which is why the tau circle shrunk to 0 smoothly in the interior. You want to replace that with an operator that explicitly breaks the winding symmetry of free theory. And so then its Lorentzian continuation will not have the tau circle, the tau circle don't shrink geometrically, so the Lorentzian continuation will look disconnected instead of connected, but it will have whatever is the continuation of the winding condensate, and that's what I want to get to in a minute. So, well, these are just redefine some of the variables to make the formula look simpler, but there's like the R coordinate. By the way, when you go to the first order formalism, there's a determinant that results in a linear dilaton for the R direction. Here I write it explicitly. And then the Z is a complex coordinate made of X and tau, and zeta is basically chi, but I made some shift in order to eliminate this term. And added to that is supposed to be a winding operator. It has to be winding in one direction plus the other direction to make it a Hermitian operator. And winding operators are not as familiar in these first order systems, but they can be written in a form like this, where this is a contour integral of this guy zeta, which is a one form on the worldsheet. So, but I don't want to get into the technicalities here, but this is an operator which carries winding around the tau direction. So if I add W plus W minus to the action, it will tell me that I don't conserve anymore the number of times the string winds around the tau direction, and that's what I wanted, because in the geometric dual, they can slip off the end. So in the paper with Elliott, we proposed this duality. It's also related to one that was discussed a while ago by Berkutz et al. And it's closely connected to the FCZ duality, but actually now, since the paper with Elliott, we, with Indranil Halder and David, made some very explicit checks that the two sides equal. Two sides here meaning this free theory plus the winding condensate equal to the sigma model in H3, or just the SL2R WCW model, which is very well studied. So all the correlators are known, or many of the correlators are known, so you can compute them here and check if they're equal. And there's technically how it works is that you integrate out the zero mode of the field R, and you can do that integral exactly, although it's a nonlinear integral. See, these vertex operators depend on, there was a factor of exponential in R that's crucially part of this, got dropped in the formula, I'm sorry. So the path integral over R is nonlinear because there's an e to the R in this, so it's e to the R. But that integral can be done exactly for the zero mode, and the effect of it is to pull down some, in general, irrational power of the integral on the worldsheet of the W operators, inserted into a computation in the free theory. And at special values of parameters, that power will be an integer power, and then it's a specific correlator in the free theory, which is easy to evaluate. And so that's how one can check this type of duality. And something very similar was done by Teschner to compute correlators in Liouville, and also to prove this FCZ duality, which is closely connected. And the FCZ duality is basically a dimensional reduction of this 3D duality, or you could say the new duality is an uplift of the FCZ duality, in the sense that if I quotiented by shift in the x direction, I will remove the x direction from the game. I'll have only the radial coordinate and tau, and instead of having ADS-Rindler, I'll get a cigar-shaped geometry, which looks like the 2D black hole. And so now the connected geometry side is this 2D black hole. Again, the tau circle shrinks in the interior. It has the linear dilaton asymptotically. That's a small difference, but comes from going on the circle. So it changes ADS asymptotics to linear dilaton asymptotics when you do this reduction. And then this kind of exotic free theory with a non-contractible time circle deformed by this winding condensate becomes the Sine-Liouville theory, which also has a winding operator. So the structure of these two dualities is very similar. This is what motivated the 3D duality. And this was checked by Teschner and others in a very similar way. Okay. So, but that sounds nice. These kind of dualities achieve the Euclidean version of this story. It says that there exist cases where strings propagating on the Euclidean black hole are identical to strings propagating in a background where the time circle doesn't shrink. So therefore, its Lorentzian continuation looks disconnected. But of course, this FCZ duality was known for a long time. What's the missing thing? The missing thing is, what does it mean in Lorentz signature to have this time winding thing in the worldsheet theory, right? How do you wind around the time direction in Lorentz signature? It's not a compact circle. What does that even mean? So that's the next topic. And I should say it's been understood at some level that what it's supposed to mean is that there are a condensate of a certain kind of strings in the background. So it's sort of like you take the background without this term. That's just a simple linear dilaton times time. When you continue this to Lorentz signature, it's some simple background with a radial direction, with a dilaton, and a time direction. And then this thing tells you that you have so you add it to the action. So that means you have many insertions of the operator. That's why we call it a condensate. But it tells you that there's some kind of additional strings added on top of this background. And the picture was that these strings are somehow coming out of the strong coupling region. They fold out from the strong coupling region. And there's been a lot of work over the years on that direction, but today I want to make it somehow a little bit more precise and try to define a formalism where one can sort of see exactly what these winding operators correspond to. So again, the picture is supposed to be something like this. So why would this correspond to a folded string? What's the idea? The idea is that, well, I guess I'll explain it on the next slide. So I'll explain it on the next slide. Let me just recap what the picture is supposed to be, and then I'll explain how you get there. One side we have the simple black hole. The other side is supposed to be this linear combination of entangled microstates. There is a background, which is produced by this path integral. That's very simple. That's just like a linear dilaton direction, space this way and time this way. But then the time winding operator is going to give some extended strings that look like these little red folds. And they will also be in entangled state on the worldsheet, and there will be a large number of them. So that's what's gives you the big number of microstates and so on. So that's sort of where this is going to go. I said this already, that here we want to discuss string perturbation theory around this particular special type of entangled state. And usually we think of doing string perturbation theory around classical Lorentzian backgrounds, but that's not quite right. I mean, first of all, even if we have a time-dependent Lorentzian background, we actually don't know how to do string perturbation theory there. And it kind of makes sense because there's no unique choice of state from the target space field theory point of view. So how is that supposed to be encoded on the worldsheet? And on the other hand, it's straightforward to do thermal string theory, like in the example of the thermofield double in ADS3 that I mentioned on the earlier slide. So what we really do is to define string theory by Schwinger-Keldysh contours in the target space. In other words, if we were, doing the target space theory, we would say that we would produce the state by making a Euclidean cap, like this blob, that defines the state. Then we have a Lorentzian excursion. Then we come back, and then we glue the other side of the state, and we insert operators on the up part. That's how we think about the path integral way of doing, some expectation value computation in Q of t. But in string theory, this is a picture of the target space. So it's a contouring field space. And actually, as a contour in field space, the Lorentzian excursion is contractible, which by general rules means that it doesn't change the theory. So we really do the Euclidean target theory and analytically continue the answer. That's the standard string theory prescription, although it's not usually phrased in this way. And if you think about it like this, it's clear what you know how to do and what you don't. You can do perturbation theory on any state that you can prepare with the Euclidean cap, and you don't know how to do the states that you don't know how to prepare like that. Yeah. So I think I already said this. If we go back to Sine-Liouville, and we could make this story for the FCZ duality or its ADS3 uplift. The rest of what I say applies equally to both of them, but sometimes it's easier to use the FCZ formula. So I'll use that, but it doesn't matter. So let's imagine that we would Taylor expand in this condensate. You can't do that for a reason that I'll bring up in a minute, but imagine you could. Then you would start with this free theory, and then you'll have a bunch of insertions of this operator. And each time you insert one of them, you'll compute some kind of correlator. Let me jump ahead to this slide, and I'll come back to the other thing if I have time, actually. So you compute a correlator that looks like this. So this is supposed to be a worldsheet computation. We have some ordinary vertex operators and one of these winding vertex operators. And we're doing the computation now in the free theory where the time circle is not contractible. This is the Euclidean computation, and now I want to try to explain what's the Lorentzian meaning. Because again, the string theory prescription is to do the Euclidean computation and continue the answer. So it's really about finding the interpretation of that computation. So when we have a worldsheet like this, normally we would relate it, if we have like ordinary vertex operators, we will relate the Euclidean computation on the worldsheet to a Lorentzian one using the state operator correspondence. So we'll say that close to any of these vertex operators, we can imagine, for example, identifying, as a way to fix the gauge, time in the worldsheet with time in this target space. And that gives you a picture of a little string moving in the target space, and the vertex operator specifies the state. But that doesn't work if you have Euclidean time winding. That's why these operators seem exotic, because if the time direction is supposed to go around the operator, you cannot make it radial from the operator. Okay? So it can't be an asymptotic state that's being thrown in, because time should go along the trajectory, but the operator says that time winds around. So instead, you want to do a continuation where we continue in this tau direction instead of in the radial direction. And a somewhat more formal way of thinking about it is that the way that we usually define the S matrix in string theory requires integral over the worldsheet moduli. When you have two operators that come together, they have a divergence. It blows up as they come toward each other. And Witten explained in a paper that the I epsilon prescription of the target space theory is that you take the worldsheet to be Lorentzian in the vicinity of one vertex, of the vertex operators. And in a sense, that justifies the fact that we use radial quantization to identify the vertex operators with some physical states of the theory interpreted in the target space. But here, we don't have a singularity of that type when they come together. Rather, when one operator goes around the other, it seems to be not single-valued, because if I have a real Lorentzian frequency, it's not compatible with the periodicity of the time direction in the Euclidean theory. And so you need to continue this tau direction, the angle direction around the operator. And the idea, the proposal is that that's the analog of the I epsilon prescription in this situation. So in other words, if we have a real Lorentzian momentum space vertex operator with frequency omega, and it comes near a winding operator, there's not a singularity, but the OP takes this form, where z is the worldsheet coordinate. So it has some exponential dependence on the angle, so it doesn't make sense. I can't integrate around it because it's not single-valued and it blows up in one direction. So we should continue the worldsheet in Rindler time, that is, in the worldsheet Rindler time. And that's a little bit, and so again, we can identify the worldsheet time with the target space time to get the Lorentzian kind of picture, but now the worldsheet time that's being identified with the target space time is the Rindler continuation on the worldsheet. Okay, so that's the idea. So that gives us something that we might call angular quantization instead of radial quantization. Let me try to find the picture of that. Here we go. So here we have one of our winding operators. Here's one with the opposite winding. We put those two in order for the answer to be non-zero, because winding was conserved to start with. And here we have our ordinary vertex operators. And now we can conformally map this string diagram, the sphere diagram, G is 0, to something that looks like almost an open string picture. We pull this guy out to infinity on the left and this one to infinity on the right. And then we have the ordinary vertex operators here. And we want to now quantize with this direction's angle direction as being time. And so we can interpret the usual string computation with these operators as taking the thermal trace on the worldsheet of a Hilbert space that you get by slicing the story this way. And now the vertex operators W plus and W minus are defining asymptotic conditions for this single string on the left and on the right. So that's the sense in which they look like strings that come out from somewhere. So we can, and so then the question is, what is that asymptotic condition? So if we go back to the particular case of the winding operator, what asymptotic condition is it associated to? This is easy to understand because we're adding it to a free theory. So everything is free, it's easy to understand what everything does. And the winding operators are of exponentials, right? Exponentials of free fields. They have the part for the radial direction, which here I called phi. Sorry, switched notation from r, but phi is r, sometimes more conventional, like in the Liouville field. And the total momentum of the operator tells you that the radial derivative in the worldsheet, that is along this direction of the worldsheet, is given by some number. And then the fact that there's winding says that the angle derivative in the worldsheet of the time variable in the target is some fixed number. So that's the asymptotic conditions. That basically fixes the charges, the winding and the momentum of this operator. And you can even write some regulated action at finite position and then take a limit that you pull it all the way out. That's the way to explicitly construct these Hilbert spaces. And with my student Nick, we checked that if you compute, say, a 3-point function of operators in the free theory, using angular quantization in this way, you get the usual answers. Although it's very tricky to go through all of the details, but at the end of the day, it all works. In the interest of time, maybe I'll just go ahead. If you really want to understand what the string states look like, right, so the point here is that because of this derivative on the rate, so what does this say? This says that we can identify the time of the target space with the time on the worldsheet, and that the radial direction is going in some direction according to the parameters of this operator. And so if we are in the case of this FCZ duality or the uplift in ADS3, you find that the string endpoints want to go into the strong coupling region. So that's why it looks like a string it looks like quantization of a string whose endpoints come from the strong coupling region. In some other range of parameters, they might come from a weak coupling region, and it's related to some work of Maldacena in 2005, where he called them long strings. Maybe we can also call these things long strings for lack of a better name, but it depends on the situation, whether they will come from weak coupling or strong coupling or somewhere else. But they're always strings defined in angular quantization with some asymptotic conditions. And if you really want to find the on-shell Hilbert space of them, you should do BRST quantization. So you have to take into account the gauge fixing ghosts on the worldsheet, and if and the vertex operator really has insertion of the C ghosts, as usual in string theory, and then they get traded into some asymptotic condition, and one can go through this whole machinery, and we're still working out exactly what you get in this situation for what the BRST cohomology of these stretched or folded strings looks like. But it's easy to see that the thermophile double state, or the thermal density matrix, is BRST invariant, because that's just saying that the time evolution on the worldsheet commutes with the BRST operator, which is guaranteed from the original closed string theory in any quantization. So it's easy to see that the thermally entangled state of these folded strings is a good physical state. It takes more work to compute what the individual single string of BRST invariant states are. So again, the picture is kind of like this. We have the one winding operator here, the other one here. We slice the worldsheet in half. And now this is a worldsheet diagram that looks very similar to the space-time picture from before. This end of the string comes from strong coupling. This end also comes from strong coupling. It folds back and forth. And the computation of the Gina zero diagram tells you to insert the other operators in the state produced by this Euclidean path integral, which is the TFT state on the worldsheet now. So it's the TFT state of a single string with that particular asymptotics. Okay, so that's kind of the answer for the single string. I think I'm out of time, so let me just sum up with this picture. So the final idea is that so that was about a single string, but the worldsheet theory has this thing added to the action. So we have to expand it out. So there is a condensate of these strings. So in the picture that this suggests, although we haven't yet fully understood it, of what the individual microstates look like is something with the radial direction with a strong coupling region, and then many folded strings that extend out of the strong coupling region. But it gives you, in a way, a machine to try to understand it. And if you put it in the specific state, which is the TFT state, in the condensate of those strings, which is what you get by adding that thing to the worldsheet action, then the Euclidean duality tells you that it is equal to the two-sided black hole. So it's guaranteed that ER equals EPR, if you like, will work in this setup. The thing that's still to be understood is what precisely, how good can we get at understanding these specific individual microstate that's not the combined thing in the TFT state. So that's probably for the future, and let me end with that. Thanks.